This video had a long history to it. It spent a long time in production. Um, so the story of this video is that oh, what is her name? I can't remember her name anymore. I only remember the name of her husband, which is very sad. But I was contacted. Well, maybe I'll keep the names out of it actually because it's a little bit personal. Like the people who know the story in the public consciousness will know who I'm talking about, but I think I'll leave the names out of it. Um, so I was contacted by a researcher, a scientist in her own right, but a woman who is married to an astrophysicist, and particularly one of the founders of exoplanet research. And she was interested. She sent me this message, and she said, "Hey, like, my husband is getting older. He's been working in this field for like 30 years. He was there like from the start of it, and we'd be really interested in like paying you to come up with like a like one of your videos that really has like tells the entire story of exoplanet research from beginning to end because it's a really cool story." And I was like, I did not know, I don't know anything about exoplanet research. Like at the time Kepler was going on, so people were always talking about, oh, new exoplanets are coming, whatever else. Um, but I hadn't really looked back into the history of it. It was just like, oh, cool, there's planets around other stars. I always kind of figured there were, but now we're discovering them. So I started going back and looking into the background to see what they were talking about, and it was really true. It was a really fascinating story about, people like a few people in the 80s who really went out on a limb, when everybody figured there were planets around other stars, but most people figured that no one would be able to see them for decades, that it was that it was it wasn't it wasn't within the bounds of current technology or whatever. And there were just a few scientists who were really, like struggling with this for years and kind of putting their careers on the line, because, if they didn't find anything, they were going to have wasted, some of the most productive years of their life and be a cautionary tale for, don't go out searching for the things that everybody tells you can't see. And it took them from the mid 80s to the mid 90s to really get there. So some of these people were, in the trenches, just trying to like perfect their technologies and get there first for 10 years. And really, given the planet that they ended up discovering first, they wouldn't have discovered, like, it was kind of crazy because they wouldn't have discovered the planets that we think exist, that we thought existed with their technologies. There happened to be these crazy hot Jupiters, that give a much larger signal, for the various methods. So it was like I looked into it and I was like, okay, this is a really cool story, and I've got someone willing to fund it, and so I'm gonna spend like a long time on this. And look at Melissa Gavin says, "You aren't tracing things with your cursor. How weird." I can start, Melissa. I can start with the ADHD tracing if I want to. Please don't remind me. So I've like Aladdin instantly popped to mind, a whole new world. But for quite a while, I thought like, well, can I do the whole story with a whole new world, like just that song? Because I'd never done like a medley before, and it just couldn't work. Like ballads are really bad for information transmission because there's just not enough words. So I was like banging my head against this and wondering how to do it, and I'm talking to a friend about it, and she suggested, well, why don't you do like a whole medley of different things? And I thought, you know what? Like I've got funding for this one. I can take some time. I can do it right. I can take a few months. So let's go. So I started working on it. This was like probably a year and a half before this video came out. I started working on it, and I got a good way through. And like the scientist who, like I kind of found a place for this scientist who had hired me to kind of be a character in the story, and that was kind of cool. It was like I was gonna try and make all of them like him, and like a bunch of the different players who were around at the same time, like specifically like named in the lyrics and stuff, and actually like tell their stories. And that was great. So I was like working on that kind of in the background while I was working on other things like CRISPR and whatever else. And then at some point, I open up my my like science news feed in the morning, and this scientist is front and center as someone who's had like a big sexual harassment scandal. And I was like, oh no, okay, what? Like now I have to think really long and hard about how I'm like whether I want to be connected to this family. What am I going to do? Because they had already like paid me some of their like they had already funded some of it. So like am I going to go ahead with it? Am I okay with them being on the funding? Am I going to send back what I can? Am I going to keep doing this project? Is it just going to be shelved? Like what's gonna happen? And so I sort of searched my conscience for a couple weeks, and like it's a combination of like conscience and like public perception, right? It's like not only do I not necessarily want to work with you anymore, but I definitely don't want to be like publicly on a video promoting you, right? So it was like definitely this is gonna need a big rewrite, and I came to the conclusion that I didn't want to accept their funding anymore. Unfortunately, like I had already used some of it in production, but like I sent back everything that I still had of what they gave me, and I like worked it out with the wife, and she, you know, we sort of agreed like, okay, like I told them, look, this is still like a great song. I'm still gonna make it, eventually, but I don't know when. I can't give you a timeline. I'm gonna have to rewrite it, and I don't really want to make it about like you guys anymore. So I so that was how it stayed, and it kind of the project kind of got shelved for about a year, and I worked on other things, and I dropped the videos that we've been watching, and then Google approached me at some point. They were doing this Making and Science campaign, and they said, hey, are there any projects that you've been looking at, like you've been trying to make that you don't have the funding to, or like are too expansive and you need more resources? Like we've been looking to fund projects like that. And I immediately was like, this is the one that this is the one that I've been trying to make, that I just like I don't have the money, I don't have the time to do it right now. And they were nice enough to provide the funding for me to spend the immense amount of time on this. And so the production got rolling again, and then like once, by that point I had already reached I don't think I had reached out to any of these guys yet, but at that point it was like, all right, time to start reaching out to collaborators, because I knew I couldn't do the whole song by myself the way it was going. It needed a few different characters. And so these are just connections that I like. Julien Neal, so I believe he's Belgian. I mean, he's one of the best barbershop guys on YouTube. His channel is called Treadbull, and just like wonderful, like harmonic, rich voice, like beautifully in sync harmonies when he does them. He's so good. So I reached out to him. He had commented, I think, on my very first video, like on Rolling in the Higgs. He had like shared it, or at least commented like, hey, this is really cool. So reached out to him, got him to be a character. Sam Robson I had been following for just ages, and continues to be my favorite a cappella person, because he just has everything. He has like the crazy dense extended harmonies that just feel glorious in your ears. He has the personality, the flair, So I was like, okay, who can I get to be kind of like that, like like genie character that'll have that same sort of energy for this song. It's like, Sam, okay. And then the last piece is, it's a whole new world. You need a duet partner. And I had connected to a couple of the Sirens, but Gia specifically, I had gone and listened to her entire like one woman show called Einstein's Girl, and she's a fantastic like Broadway style singer and composer and everything. So I reached out to her on Twitter, and they all said yes. And so I sent them, I think I just, with this too, I sent them just like beats and piano tracks, and waited for them to see what they would send back. And yeah, they all kind of blew it out of the water. We had to figure out, Julien has he has such like a piercing, like not piercing in a bad way, but like his resonance is so strong that it was really hard to like figure out how to have him sit in the mix with my vocals. So we went back and forth like a whole lot with him, because he was like, no, this like, I'm not fitting in here. And I was like, yeah, you're totally right. Let's see how we can like soften you and bring me up. Because the part I wanted him in was actually a part with, like, for part of it had very little harmonies to it. Like I wanted it to pretty much just be bass, like the Pega C51B. and it took a while to like sort of massage that into something we were happy with. Sam sent me back, you know, I sent him like kind of a genie-esque like track of what I was thinking, and what he sent me back was, you know, him going off the rails in all sorts of cool directions and changing it up, and also like various backing vocals that I could pan in different directions to get these effects, like stereo effects, and just like he's a real producer. He knows exactly what he's doing. And they were just, you know, they were just all great. And you know, Gia has that like she's I watched the duet part, and I'm like, man, I look so, you know, green and awkward, and Gia's, you know, this she's expressive, and she knows what she's doing with her face, and she knows how to be in front of a camera. It's so much nicer to have like other people in the front of these things. That's what I've come to understand. Like whenever I can have someone else doing the lead, I feel way more comfortable like watching my own videos, because I can just be like, that person's so cool. I love watching them. I don't have to worry about watching myself. So there's the background. We'll probably get into a whole lot of exoplanet science as we go, but let's kick it off and watch this thing. A whole new world. A whole new world. That's what we'll see. That's what we'll see. I think this, the reason why this is colored in the particular kind of brown it is that Julien didn't have a green screen. All the rest of us were able to shoot on a green screen, but Julien doesn't have one. So he shot on a wall, and then I'm blocking Gia. I'm sorry, Gia. For now, you're going to be like that, but you'll get your moment to shine later. She's going to be over here later. Julien had this wall, and the only way that I could figure out to get us all to look in the same background was that I like clipped his wall and actually put it behind the rest of us. So that's Julien's wall over here. So you're hearing the electro swing come back. I'm looking for one tug, the pull of the planet. So this is like the main, like the scientist character. I think this was originally supposed to actually be that scientist that I had hired me, and I have, you know, I had like references to him in the lyrics and stuff. But in the end, I like it a lot better, because this is kind of a composite of a bunch of different like characters from back then. One tail, a wobbling sun. I've searched for years, haven't found a one. They're out there. One jump in radio redshift. One slip, spectral lines. They'll see if I can show them the signs. Okay, so there's, I mean, I don't know how obvious this is, but this is the first method that they had for detecting exoplanets. So you've got the equal and opposite forces are Newton's bread and butter. You often think of the planets as going around around stars, but in fact, if a star is going around the planet, the star is pulling on the planet's also pulling on the star, and it's pulling it around in a little circle. So if you've got a planet, if a star's got a planet, it's going to wobble in this little circle. And there's this thing called the Doppler Effect, which is that it's what happens when a motorcycle goes past you and goes. While something is coming towards you, frequencies of vibrations are squished because it's coming toward you. The wavefronts bunch up. It's racing them, so they all get kind of squished. And as it passes you by, the wavefronts move further apart because it's emitting them backwards. But every time it emits a new one, it's further out that way. So when something's moving towards you, frequencies go up. And when something's moving away from you, frequencies go down. And so that the same thing happens with light that's emitted from the star. And there are these in the spectrum of a star, so like the frequencies of light that are emitted, it's what's called a Blackbody Spectrum, which is kind of a weird name given that stars are not black. But a Blackbody Spectrum means that it's just like a thermal emitter. It doesn't emit any particular frequencies. It's like a glowing stove or whatever. It's got a very broad band of frequencies. In a particular shape. I'm hitting the microphone. And that's what a star does. But there are particular elements and compounds in its corona, in its atmosphere, that will absorb very specific wavelengths of light, because every molecule has a few particular wavelengths of light that it likes to absorb. And so the star is emitting in all wavelengths. That's why you get a rainbow. but there are certain molecules pulling certain ones of those wavelengths out. So there's going to be a gap in the different colors of light that you're receiving as you look at the star. So that shows up as if you make like this is basically just a really fancy prism, this kind of thing, that there are these things called A-shell spectroscopes, A-shell spectroscopes, or A-shell spectroscopy. And let's see. Yes. Someone's telling me to look in the chat. The first one proven to exist was not Pegasi 51 Pegasi. No, it was around a pulsar, but we didn't like it. I think I actually mentioned that in this song, that there had been one discovered, around a pulsar before, but the 51 Pegasi was the one that really changed the news and made it, and like made the news and changed the game. Anyways, so as your star wobbles around, it's moving away from you and then towards you if the planet's in the right plane, and you'll see a little bit of wobble in these lines on your rainbow. If you got a really precise instrument, you can use that to figure out how fast the planet's going around the star and how much it weighs by the amplitude of the wobble. And that's how it's done. But it was incredibly difficult.
Pish tosh. Green man.
Okay, so let's back it up a bit. Oh, where am I? So this is, I hope this comes off clearly that this scientist is like the super earnest, trying to make this discovery, and then you've got these bigwig scientist types. I think I actually credited them as the bigwigs, like these are like funding agencies and stuff, that just won't give them the time of day and won't give them any funding, which is very true. These guys did this stuff on like a real shoestring budget.
See if I can show them the signs.
Pish tosh.
Green men.
Take 5. Take 10.
You will notice these different logos. You can't really see here, but this is supposed to be, it's A's all around here. So A, I think this is modeled after the NSF logo. And then
Green.
Capella, this is modeled after the NSERC logo. The Canadian one says Capella. And then Science, I believe this is like the British, so I was trying to do like the various funding agencies, but also subtly shouting myself out, I guess. We've got, I'm not sure why Julien went with this like crazy clown outfit, but I like it. I don't know. It adds to the color of the whole thing. It was really hard to cut him out of here because once again, he didn't actually have a green screen. So this is like rotoscoping.
5. Take 10.
Just a little cash, guys.
Budget's tight, don't fund this trash guy.
I love Gia there. So good.
I can take a hint, better face the facts. Second hand will have to do.
This is like the same thing that I did with CRISPR. I pretty much just copied it with this setup here. It's exactly like that, like blue light thing. And then Gia sent me this, and I tried to like copy exactly what she was doing so that we could be in sync.
Finding planets, except they haven't got one.
Well, they gotta be forming readily when you think about it, given we've got 9. One jump, blip in the spectrum.
There's our is Pluto a planet argument again.
One shift, meters per second. One graph, period power.
So, okay, here, this takes a little bit of explaining. It is, these signals are very noisy because like we were talking about with the LIGO video, they're affected by also, like, if you're trying to get a vibration that's a very tiny magnitude, your noise is going to be anything that causes a vibration anywhere. So for LIGO, it's like distance vibrations, so it's like the planet, like, I don't know, tectonic activity and trucks rolling by and whatever. For this, it's stuff like they're doing these observations from, like this wasn't space-based. They're doing these observations from Earth, so there's aberrations from the atmosphere doing things, and then there's noise in their actual equipment, and so it's very hard. So it's very hard to like pull a signal out of the noise, and you also don't know what you're looking for. So like you're trying to automate this and like put it into a computer, and then you don't know what you don't know what kind of cycle you're looking for. It could be a 2-day cycle, it could be a 5-day cycle, it could be a year-long cycle, right? And so what you do is you take your whole signal and you Fourier transform it, which means you take this big, jittery signal of that looks like a stock market thing or whatever. This just seems to be going up and down randomly because there's so much noise, and you break it down by its frequencies. So this is what your ear does to listen to music. It breaks things down by its frequencies. But you do that, and you hope that you see like within that crazy noise some sort of periodic spike where it's like, oh, that frequency is more prominent than everything else. So like if you were to hear this, because this is a period of in this graph, this is a period of like, I don't know, 60 days or something like that. But this is also the kind of thing that you could actually turn into music. It would probably be like a noisy tone. So it would have like a to it, which is this peak, but all this stuff around it would just like be kind of this white noise. I mean, I don't know. It would be really cool actually to turn like spectroscope data into music. Maybe I could do that. Probably someone's done that.
They laugh, but I'm not sour.
Oh, and then here's how the Echelle spectrometer works, which I don't think I remember in detail. Like it's a lot like, it's basically a very fancy diffraction grating. So I don't know if you've ever seen, you can do it on your phone actually. Your phone acts as a little diffraction grating. If you kind of point it right at a light source, you might notice that you get kind of, especially if it's turned off, you might be able to get kind of these like crossed rainbow patterns that are both vertical and horizontal, because your phone is like a two-dimensional. It's this little two-dimensional grid, and grids interact with light. If they're at the same sort of like spatial frequency or spatial resolution as the wavelengths of light, which is hundreds of nanometers, so like a bit less than a micrometer, then they can interfere with certain wavelengths of light that are at those that are around those resolutions and reflect them preferentially at particular angles. So you'll get this rainbowy effect. So it's the same thing as rainbows being diffracted in different ways, but it's using tiny little structures instead of changes in speed of different wavelengths or whatever. So it's I don't know all the details. They're using mirrors to like amplify the amount that it moves and stuff, but light comes in from a particular star, and you have to try really hard to block out everything else, so you're only getting light from that one particular star, which is really difficult. And then you try to lengthen the path of it, so you can amplify how much spectrum it does. And then what you get at the end, there's also like, they're taking the spectrum and they're actually mapping it out into 2 dimensions by using this really clever technique, because a diffraction grating, like a rainbow, like if you've ever seen a double rainbow, there's like a first set of angles that light diffracts at, but then there's like a second set of angles. In a rainbow, I think it's because there's like double and triple bounces inside of raindrops. I could be wrong with that. But in a diffraction grating, it's because, I've got, hold on. I need to plug in my, oh no! Hello, are we back? Somebody tell me that we're back. I'm gonna keep, hello? Are we there? Are we back? A Ruchiaxlotl says we're back, I think. Cool, we are back. Let me just confirm. Yeah, my laptop impromptu died. Let me make sure that we're also back on YouTube, because I can't currently see the YouTube chat. What on earth? What is going on here? Someone tell me if we're also back on YouTube. Okay, cool. YouTube is back too. Okay. I can't see the chat on YouTube, but I'm gonna keep going with it. That was awkward. Sorry guys. It was once again that same thing where I completely forgot to plug in my laptop before I started streaming, and it died, and I ran over to get it plugged in. So luckily we got it. Cool. Yeah, so what was I saying? This A-shell spectroscopy, it's actually really cool because it's using this like double, like with diffraction gratings, you don't just get two, you get like every multiple of the wavelength or the angle, whatever, like diffracts the same way, and you can get really high diffraction numbers, like all the way up to like 10 or 100 or whatever. And so the A-shell uses all of those different multiples, and it spreads those out just a little bit so that they fall on like a 2D plane. So up here will be like diffraction number 75, 76, 77, 78, 79, 80, or whatever. And that way you can project this whole thing onto like a 2D screen and capture it with some sort of like digital camera setup. And it works really well. And that is how they were able to do it. I think it's called A-shell because this is like a ladder of different spectra. They're all piled on top of each other. Yeah, anyways, the more you know. And also it just makes a really cool looking background.
Here goes 18 months of data cross and correlated. All I gotta do is run!
That's a little hammy. It's a little on the nose.
Pish-tosh, green men, I don't mind them. If only they'd look closer, would they see a pure void? No siree.
Pure Void. I told you Pure Void would come back. Remember Bohemian Gravity? Space is a pure void. And then these guys, if you listen to them in the background, they're doing the same thing. Ooh, space is a pure void. And he's saying, would they see a pure void? No siree. Looking out into space, they would find out there's worlds galore.
Would they see a pure void?
I'm too proud of myself.
They'd find out there's worlds galore to see.
That was a cool chord. What's that chord? It's a B. It's like a B minor, B minor 9 add 6 or something. All these graphics were from like NASA's website, I think. So now we're in 1995. The discovery of Pegasus.
First was a world on an old pulsar that's...
There you go. There's your PSR. I can't remember the name of it, but the first planet was actually around the pulsar. But that's true. But the news is a sun-like star.
But the news is a sun-like star with
Listen
bubbles
to
of quick
you,
and precise
man.
to be designed.
That resonance.
No fluke, not a spot. If you like it hot, you're gonna love this find. Pegasus 51b, planet discovered. Orbit traced every 4 days, hot as can be. Its order, Jupiter size, was something of a surprise, especially given its star's proximity.
So like this is a really good like I don't know, it's a really good argument for go and search for things and do like basic research in a lot of fields. But like as soon like people were like, okay, we can't search for exoplanets because we know what kinds of planets there are. There are like the planets that are around our stars, and you know, like there's the little ones are further in and the hot and the gas giants are further out, and that's probably how every planet, every solar system is. And there was like this whole like theory worked out as to why our solar system had to be that way, right? Like that, oh, there's these particular dynamics that causes definitely all rocky planets to be closer in but at like this certain distance, and gaseous planets to be further out, and like these mathematical ratios people were trying to work out of like that were based on our solar system. And then they go and look, and the first planet they discover blows everything about that out of the water, because it's like a Jupiter-sized planet that is closer to its star than anything in our solar system. It's going around every 4 days, right? And that's crazy. It's like super hot. It makes no sense. And like with one observation outside of your own system, you've thrown out like decades of hypothetical theorizing. And that's like a very similar problem now that we have with a lot of things in physics where we only have a sample size of one, like the laws of physics, or the like a lot of stuff in cosmology, like why is the universe the way it is, why is it expanding as fast as it is, all that kind of stuff. We only have one sample, and a lot of physics, you know, like people sort of fall into desperately trying to like find why exactly it should be this particular way, and like that it's determined to be this way. But if we've learned anything from exoplanet research, is that when you step outside your sample, sometimes you were a random happenstance, and there's like a whole different bunch of ways that you could have been. Yeah, 51b, Pegasi. Okay, so it's I have a hard time following this even. But we're doing a lot of information. When I'm watching this, I always tend to focus on me and Gia doing this thing. So I always miss what Julien is saying. So what we're saying is, how did a planet get so close in orbit? Because I thought you needed ice to form it. So that was the current theory. That was the theory at the time, was that like Jupiter-sized planets could only form with like an ice core in the outer solar system that had to be a certain distance away, and then you'd have like gas coalesce around this ice ball, and that doesn't work if you're forming that close to the sun at a orbiting time of 4 days. So I'm not sure what the current status of the theory is now, like whether people have figured out how hot Jupiters can form close to stars, or if it's just like some stochastic thing that something actually does get kicked in from the outer solar system into a very close orbit. I don't know about that. Maybe they're captured planets, you know, like but we found a whole lot of these afterwards. Like they were all the first exoplanets that were found were hot Jupiters. I mean, there's a selection bias effect there because they were the only ones we could see with that technology. Because if you've got something really big and really close to the star, it's going to make a massive wobble, and that was the only thing that was getting above the detection threshold. But even so, like it's, you know, takes explaining. So that's that. And then what is Julien saying? Oh yikes! What on earth? You guys hearing that? Are you hearing that horrifying sound? This is gonna require some clipping, I think. Yeah, let's go back. It's a new era to detect exoplanets. Soon there'll be 3. Yeah, so that's one. But so very soon after that, I think it was Mayer and Kalo that made this original detection. They ended up getting the Nobel Prize for it. Start over. No. We're gonna
as planet falls on its sun, it shifts the stellar spectrum. That's how we find the thing.
Oh yeah, that's the other thing with this discovery. Because it was so wacky, there was a whole like spate of people just trying to disprove it, writing papers like, no, it's not a planet. It's like the star is spinning at a rate of 4 days per second. You're just seeing a sunspot, or or it's like a pulsating of the star, because there's like these stars like Cepheid variable stars that pulsate and stuff, and that's affecting your measurements. But it was too small to be pulsating, because pulsations are dependent on the size of your star. You know, like anything that's bigger takes longer to act. You know, a whale's heartbeat is longer than a mouse's heartbeat. So it was too small to be pulsating at that period, and too old to be rotating that fast, because they fling off angular momentum through like dust and stellar atmosphere and stuff. And I was like, nope, this is the only possibility.
We got your funding. We got your funding. It's treacherous, so treacherous.
On this new breakthrough feels Monday.
Proof of the truth I've been telling you.
This is so mean anomaly.
The mean anomaly is actually a technical exoplanetology term. I think it refers to, what does it refer to? Is it part of orbits? someone who's into planets, tell me exactly what mean anomaly is. I think it's the difference from, it's either the difference from a pure circle or the difference from a pure ellipse. I don't remember which one. Anyways, this is no mean anomaly. I thought was an interesting double meaning.
Anomaly, Pegasus,
The mean anomaly is the fraction of an elliptical orbit's period that has elapsed since the orbit passed periapsis. There's more terms in there that I don't know than explanation. What's periapsis again? I should go back to school and remember how planets.
51B planet uncovered. Round of 4 main sequence star spectral type G.
Do you know about all the spectral types of I should do a video about like all the types of stars. I should do an all-star parody of all the different types of stars. That's a good idea. Shelve that.
You know its mass to be high. Half Jupiter by Sinai.
Half Jupiter by Sinai, because you can't, so the mass of a planet, like you can't actually figure out from these stellar measurements, like these spectrum measurements, what the mass of the planet is. You can get a range, because if the planet is rotating like within the disk that you're observing, star will go around in a circle. And there's actually another technique called astrometry that was tried to see stars going around in the circle, like within your plane. And I don't know if it's ever succeeded. I think that comes up in here. But this one only really works if your planet is going around like this, so that the star is coming towards you and away from you, so you can get that Doppler effect. But if planets don't just decide to be on particular axes. So some stars have planets going around in this direction, and some are going around like this direction, or whatever. And the angle of alignment of that to you is called I, in the lingo. And so if the that's going to affect how, like, your measurement on how massive the planet is, right? Because if a star is moving towards you and back a little bit, you could imagine that it's a small planet going directly around in your line of sight, or it's a very large planet with a very high angle, and you're only seeing a tiny bit of shift because mostly the star is going up and down. So that gives you like an upper bound, or it's like a lower bound on how massive the planet is. So they knew that it was high mass, but they didn't know whether it was, like Jupiter or like super Jupiter, right?
It's 50.61 parsecs from home, and it checks everything how planets are forming. It's stars and Pegasus, give it an A, and thus the name of the planet is B51 Pegasus.
I really like that throwing in that primer there on like why we actually call these planets these weird names, because I did not know that before.
Ships glacial pace and that astrometry never prevailed.
Yeah, so this is astrometry, where you try to like see the star going around in the circle and like measure its distance to 3 other stars. But it's just such a tiny, like compared to the size of the star. These stars are going around by like, tens of, at most like hundreds of meters, I think. It's like really like at least meters per second. It's not meters total, but like their speed is like 10 meters per second or something like that. And it's just like ridiculous to try and actually look out a light year away and see the star moving. The spectrum is a much better is a much better sense of it. So we can do astrometry with Gaia now. Okay, cool. Sweet. But yeah. So at this time, we're at 2009, and this is we decide to get up beyond the atmosphere. Now exoplanet research is like properly funded, right? And it's like, all right, let's send Kepler up into space and have it stare at one particular spot and see what it sees.
Baby, you're in luck, 'cause up in space you got a plan to find it never fails. You got the power of statistics now, you got a view of an atmosphere. So no, when I spend locked up in your tower, all you gotta do is read right here, and I say,
man,
Kepler.
He's so good. Ugh, man, Sam, I got to get him on here sometime. We keep wanting to have conversations. We've never actually spoken, me and Sam. I'm like a Patreon supporter of his. We've done a video together. We've never actually had a conversation. There's been like 2 or 3 times where we've said like, hey, let's like get on Skype and chat and like do other things. And then I always like forget or something happens and I've never actually got it to work. So I don't know. I should see with that.
The planet search, you gotta tip no 2, no 3. We just measure brightness, plot it out, and that's transitive photometry. Hey!
I really like that rhyme, transiting photometry. I feel like I don't have to explain it because there's so many, like in this section, there's so many of these graphs that give you a sense of what's going on. You know, you're measuring, but like this is, if this is a little confusing, this is the total light output of the star. Like you're not actually seeing this. What you're seeing is a tiny, tiny little pinprick of light where all of this, like the actually resolving it is like way beyond the resolution power of your telescope. You know, you would need a telescope like the size of the planet to get a view like this of a distant star. But you can just take in all of the light at once, and if you get a little less light, then some of it's being blocked by something, and if it has, you know, like a periodic pattern, it's like, oh, well, it must be being blocked by something that's going in front of it every every year or month or whatever it is. So yeah, this is a graph of like total light output that you're seeing in a particular star. So what Kepler did was it just like went out into space and it just stared at one spot. It was fixated on one spot in the sky. I think it still is. Actually, I don't know what's the status of Kepler now because it had one of its control wheels broke, and I think it could still be used with one, and then the other one broke, and they're still getting some use of it out of it, I believe, but it's a lot harder to actually point it in. You know, like it long outstayed its planned period. I think it was planned to last for 5 years, and it's still actually being used. Oh, Kepler's shut down now. Okay. When did it shut down? Do you know? Because I remember it was, people were talking about it still doing some stuff not too long ago. I don't remember. I didn't hear about it being like fully shut down. Yeah, but like now when you look at when you look, it's funny because when you look at like the like sky map of all of the stars, that all the exoplanets we've discovered, it's like there's like little dots all around the sky where like people have happened to point telescopes. Oh, back in 2018. Okay. November 2018. And then there's this crazy dense cross-shaped region in a particular part of the sky that's just covered in dots where we found exoplanets, right? And that was just because that was where Kepler was looking, and it's perfectly like that region of the sky is perfectly matched to the viewing of like the viewing shape of Kepler, because this is see if I can find it. Yeah, so this is what the detector looks like inside Kepler. It's it's all these, it's basically like a giant digital camera, but this is what the sensor looks like, and they had to, I'm not sure why they had to block off these 4 regions, but I'm sure there's a very good reason. So now on the sky, if you look at these maps, there's just this shape in like brilliant blazing data. So imagine how many stars we have not observed, because this was not, I think this is like an area, I don't want to speak out of turn, it's not a very large area on the sky.
No 2, no 3, we just measure brightness, plot it out, and that's transitive photometry. Hey, my, whoa, no, got a planet there. When your stars do this, and your curves displace, then your star's got this, transit in his face, then you hit compute. Looky here.
I imagine it's actually a little more difficult than just hitting a button that says compute. Imagine if science worked that way. You're just like, collect data for several years, large button that says compute, press it, get all of your planets. That would be awesome. This is actually though the like the Kepler table from Kepler's website, showing like all of the confirmed planets and candidate planets and stuff.
You get good diameter data from the dip, and orbit distances from the left foot.
Yeah, I mean, the larger the dip, if you get a bigger thing going in front of the sun, you're gonna get more of its light occluded. So you can get, like, Kepler doesn't actually get much information on the masses of planets or their densities. Like they have like the rough diameter of the planet, and then they have its orbital period, because that's what you can tell from like an occlusion method. But and then if you can get it confirmed on the ground by, so one of the things he says next is like, you usually these planets are like, from Kepler they're considered like candidates for being planets, and then they go with a ground-based like a shell spectrometer, and they point it at them and like see if they can see if they can see a wobble of the star, because now they know exactly where to look and what period to look in and stuff, and that'll really confirm it. And that's when you say you've got like a confirmed exoplanet. But even so, like there's a lot of play in like what the densities of these things are. Is it density? Is it just materials? I know, like, so for exoplanets, like, yeah, with the shells you can get the mass. With the spectroscopy you can get the volume, so you can work out the density. And so this is when people come out with things like, here's this Earth-like planet or whatever. They know it's the right size and they know it's the right mass, but you don't actually know what it's constructed with, right? Like you don't know if it's rocky or if it's a combination of like metal and water, or like there's a whole bunch of potential possibilities for what kind of composition a planet might have. So it's and then with larger planets, like I think with gas giants there's also a lot more. Let's see, it's density and teen. There are debates about, and then there are debates about the material. Yeah, because like there's lots of different material compositions that can give you the same densities. So people argue about whether, is this a rocky planet? Is this like a super Earth, like a large rocky planet, or like a small gaseous planet? And yeah, there's a large overlap between those regions. There's the shell again. We got 2,000 planets certified, 2,000 more than only time will tell. I don't know what that number's up to now. But let's take them all and plot them out and find out if we're really all alone. But you can see this is, I think this has more to do with the sensitivity of the instrument than the likelihood of having a particular planet in that particular region. So this is it's a bit cut off. Maybe does it zoom out? No, it doesn't. This is orbital period. This is the radius of the planet. So you can like this. Actually, you would expect that you would preferentially see planets with higher radii in this thing, because they would stand out like mad, right? Like there'd be a huge occlusion shadow. But stuff with low periods, you're going to see a lot easier and quicker, because as soon as you've been observing for, like 10, if it's 10 days or whatever, as soon as you've been observing for 20 days, you're going to see a repeating signal. Like, okay, we've got it. Whereas if you launch this in 2009 and you want to confirm a planet with an orbital period of 3 years, you've got like, if you want to confirm a repeating period, you've got like a few periods to go by to get good data. You're probably going to need like 10 years to do it. So that's one of the reasons why it took like quite a long time to, like, the first planets they found were all down here, and then over time we started to like shift down into this region. So this is us, 1 Earth radius and 300-day period. And there is, you can see we've got to like first quarter. Oh, we can actually see how it transitions. We got 2,000 planets certified, 2,000 more than only time will tell. But let's take them. Yeah, so we start with these ones, like in this red region. This is Q1 to Q6. I think that's years of operation, but or quarters, like quarters of a year. I'm not sure. And then lay on more, and then as you can see, as we observe for longer. This pink one down here. This is like the first one that we ever get as like that's an Earth-like planet. Woo, big discovery. And then as you keep going even longer with Q16, you start to get more down populating this region too, because it just takes longer to see them. So even the habitable zone is like a variable It's a variable region with a lot of play in it because it's supposed to be the zone where liquid water can exist on a planet. But as we know from lots of from the past couple decades, the temperature of your planet can be very related to the composition of your atmosphere and all sorts of other things. So like the Earth has been a snowball a few times, even though it was at the same orbital the same orbit from the sun that used to be. Now it's warming up, and there were times in the past where the Earth was a good 10-15 degrees warmer than it is now. And so it's like, Venus is hotter than Mercury, for example, because it has its dense atmosphere, even though it's way further out. So like, it's kind of tricky to tell whether a planet is actually like where a planet is in it, like in relation to its sun, doesn't actually tell you the temperature on the surface of the planet. So there's like this wide region of maybe it could be, right? There could be liquid water on here, and that's all the habitable zone means. Yeah, Kepler 452b. I'm not sure if that was the first, but at least when I did this, it was the most interesting candidate.
Never been a field clever as the field there ain't never been a field better than a field they call exoplanet.
Look how much fun Sam was having in that part. That's so like he just every time he does a video, he just like lights up for it, and he puts like 100% of himself into it. Go and show Sam Robson some love. So then this was state of the art at the time. But in 2016, we had discovered this planet around the Proxima Centauri, or Alpha Centauri, which is like our closest star, which I thought was pretty cool. Proxima Centauri is our closest star, but the Centauri system is a binary. I think it's actually a trinary system. But Alpha and Proxima are like orbiting each other.
I can show you a world, a shining, shimmering planet, found concealed in the band shifts of the closest star in sight.
Is it trinary or trinary? Yeah. Did I have an exciter on my voice, or had I just? I think this might have been the video where I learned how to Alpha A, Alpha B, and Proxima Centauri. Okay, so it's Alpha A. Is it Alpha A and Alpha B that are like really close orbiting each other, and then Proxima is orbiting around both of them? I think that's how it works. Now that you point out that there are three, that would make sense given the naming scheme. Someone confirm that for me. Ternary? Maybe it's ternary. Yeah. Okay. Cool. Yeah, I think this might have been the video where I finally figured out, because actually at the beginning of this, if you listen to the timbre of my voice between the beginning and the end, because I recorded the beginning like probably a year before the end, sometime between there, I figured out how to go from like a whole new world, that kind of sound, like I can show you the world, which is like exaggerated, but like you give a lot more twang to your voice. Or maybe I was cheating and had figured out vocal exciters at this point, because there are things you can do to vocal production where you put on like basically like a soft distortion on those particular frequencies that people really like as like a healthy vocal twang, and you just fake it. That's actually why people like old tube gear a lot of the time when they're doing audio production, because it'll distort the voice in a way that people find like, I don't know, pleasant, like a super stimulus. Anyways, I was doing something. My voice sounds pretty good. I look weird. I look pretty awkward, but the voice sounds good.
And I found hope in the skies.
Like overacting, kind of.
Wonder, I wonder, could the sine wave discovered be a planet fit for life?
So yeah, so this one was also discovered by that old like spectroscopy method.
A new fantastic point of blue, placed in that narrow zone where water flows.
Oh, it was around Proxima. I'm like, I haven't watched this in so long that I'm forgetting the actual science. So it was Proxima b. Yeah, so it was around Proxima Centauri, which is literally the closest star to us.
Midway between cold and steaming.
A whole new world. Its sun of faint and reddish hue. Could there be waiting here a biosphere evolving in this whole new world to
Fathoming a whole new world to view.
unbelievable find?
There's a lot of this. Like, I listened to the original Whole New World a lot, but at the same time, like, I don't think I really followed exactly. Like, it wasn't like Animalia where I actually got like the music sheets and sang every part as it was in the orchestra. I kind of ad-libbed it and like just did like orchestra things that sounded interesting. But there's a lot of like string runs and stuff in this orchestration, like, and it's like you just kind of wing those. And what I've discovered in doing like orchestral things is that when the notes are that fast, no one cares what they are, no one notices what they are. You can just like put a whole bunch of runs together that like in different parts that don't make sense at all, and they'll add up to be something that feels like it's just kind of pushing in the right direction. And then as long as you like all land on the right chord, it sounds like it was exactly what you were going for, and it works. So
World to view.
let's hear that run again.
Could there be waiting here a biosphere evolving in this whole new
So I listen to the background here,
Fathoming a whole new world to view.
and then it just kind of arrives.
Indescribable feeling.
Yeah, so now we've found that like it's pretty unlikely that Proxima Centauri b would be habitable. It's like, yeah, as Yan is saying, it's basically Tatooine. It's like it's a dwarf star. It's kind of like people don't think that it would be habitable, but at the time, I don't know. At least when I wrote this, like everyone was kind of breathless about it, and I also took a little bit of creative license, I think. Yeah, what's Error of 86 saying? Unfortunately, Proxima is an early M dwarf, very magnetically active, right? Late M dwarfs are much better candidates for habitable exoplanets. Yeah, but wouldn't it be nice? Wouldn't it be lovely if the world was full of hope, and then that hope gets taken away from us by the brutal realities of actual science, which is great. Continue to do that. Have hope, let your hope be dashed. Recover your hope and apply it to new things.
Earthling someday revealing through directly captured light a whole new world.
Don't just stare from afar.
So this is what are we talking about now? We suddenly, like, in the second verse we're like projecting into the future, I guess, because so far there have been a couple actual observations of planets, like optical observations, but where you can actually take a picture of it, but they're real stretches. It's like it'll be a planet that's like way out, absurdly far from its star, and so that you can actually block out like the general problem with trying to see a planet around a star is that the star is just so bright. It's like trying to see a firefly next to a police lantern. Like it just gets totally swamped out. So you have to figure out very clever ways to block out the star. And so like the only ones that we've seen so far, I believe, it might have changed since, but have been where you've got like, for some reason, a planet way out, like absurdly far, but it's also large enough that it makes a good reflection. And then you can nicely occlude the actual like solar light and just focus on the planet. So you might have seen that like Eye of Sauron picture with a planet in it.
A whole new world.
Don't just stare from afar. Wouldn't close up be bolder.
Next to its parents' fair. If life is there, we'll know through atmosphere
A whole new
spectroscopy.
Okay, so there's a bunch of stuff going on here. So atmosphere spectroscopy. This is something that I went to when I went to this perimeter conference called Convergence. I was already thinking about this. That was like when I was doing the Pluto video. But there was an exoplanet researcher there named Sarah Seeger, and Sarah Seeger is like she's like a genius, and she talks twice the speed of everybody else, and it was just like a fire hose of information. Her like her lecture there, but the Gia's eyes, yeah, pretty great. But like most of this last, I'm really glad I happened to go to her talk, because most of this last verse is from her stuff. So the interesting thing about finding life on other planets is that it's really, really hard, because if you can't even see an exoplanet because it's blocked out by the glare of the star, how the heck are you supposed to see whether there's trees and sharks and whatever else on it, right? Seems impossible. But it's not that impossible if you can see the star if you can see the planet in the first place, because like happened when you saw those absorption bands in the star's spectrum, those bands will also exist in the reflected light off of the planet, and they'll have absorption in all of the chemicals that are in that planet's atmosphere. And there are certain chemicals that just don't show up in an atmosphere unless there's some sort of ongoing process, like ongoing renewed chemical process on Earth, or on the planet, producing them and like pumping them into the air. So like the example on the like largest example on Earth is oxygen. Oxygen doesn't stick around in an atmosphere. There's no oxygen on Mars. All the oxygen, well, there's lots of oxygen on Mars. You know where it is? It's in the ground. That's why all the rocks are red. It's the rust. All of the oxygen is reactive. So if you leave a planet with a bunch of oxygen and no life on it, the oxygen reacts with everything on the surface and it goes into the ground and you're done. No more oxygen in the atmosphere. And so the only reason our atmosphere has oxygen is that we've got these, this life is, it's chemical reactions that are resisting equilibrium, right? We're taking free negative entropy from the sun. We're using it to keep us, and by extension the entire planet, away from its equilibrium state, and that allows there to be compounds in the atmosphere that wouldn't be there otherwise. So if you look at another star, at a planet around another star, and you see an oxygen atmosphere, it's like, oh, like either there's life there, or there's some really bizarre geological process constantly producing oxygen that we've never heard of, but it's at least a pretty good indication. So what Sarah Seeger was trying to do was like generalize that, right? Because we don't know how life on other planets might work, and it might not use oxygen, but it will probably be it's some sort of disequilibrium process. It's probably going to be pumping excess something into the atmosphere. And so they were looking through like thousands of different chemicals and just trying to see like, what are all the possible signatures that you could see in a planetary spectrum, and that would be an indication of some sort of non-equilibrium is happening there, and then you can like focus your efforts on that. So that's what's going on here. She's saying, well, if life is there, we'll know with atmosphere spectroscopy. And then in the meantime, I'm going off on this. Oh, what is it called now? The Starshot program that had, I think, just been announced as well. Who are the billionaires behind Starshot? It was Hawking and this like Russian billionaire whose name I can't remember now. The idea being to break through Starshot, yeah, to use like a huge, like, I think terawatt or some absurd multiple terawatt laser array on Earth, to Yuri Milner, yeah, that's the guy, to in combination with solar sails, which are usually very slow, but if you've got like a massive bank of lasers pointed at them, and a very small payload could actually become very fast. And I think there's still, I mean, I don't know how it's going these days. I haven't really checked up on exoplanet research in a while. That's one of the things I'm realizing commentating this video. But the idea is that if you've got like a 10-gram payload or something, you can accelerate this thing to close to the speed of light in a fairly short amount of time by just pumping immense amounts of laser light onto it, because light carries light is moving energy, it carries momentum, and as it bounces off of a reflective surface, it's carrying momentum in the other direction. Momentum has to be conserved, so it imparts that momentum onto this screen and propels your craft forward. So you focus all your lasers on it as it's going out. You keep them focused right on that spot, and then hopefully you can get your probe shooting out at something like some appreciable fraction of the speed of light anyways. So I'm talking about that over here. And then Gia is also going to talk about the Sunshade, which is another thing that Sarah Cedar introduced to me in that very same lecture, which is basically what I was saying before about blocking out a star so you can observe the planet. But you can do that like with a little, like the easiest way to do that is to just put a little disc inside your telescope so that as the light comes to you, it's blocking it out. But if you work out like mathematically the best shape to block out the light from a point object so that you can see around its periphery, it turns out that the best shape is this weird like flower type shape and you have to put it like hundreds of kilometers away from your telescope. So the idea with the Sunshade is that, or is it Starshade? Starshade or Sunshade? Is that you launch this flower occluder that you launch it in a little probe and it opens up while it's in space and flies out like a couple hundred kilometers away from your space telescope, and you line them up so that you have the telescope pointing at this flower shape and blocking out whatever star you're trying to look at, and then it just sees around the periphery and because of its particular shape, all of the diffraction kind of lines up to give you a really nice image around it at like a Earth type distance, so you can actually see planets there. So that's what people are working on. It's not launched yet. It's still being sort of like, I don't even think it's been built. Like there've been scale models built of this thing. But I don't know if it's got like a launch date or if it's even approved to actually work. It's still being tested. Yeah, so Brett, this is what we're talking about.
Laser Starshot to pursue, chasing that.
So like all that explanation for like one line of dialogue, eh?
Crazy dream that's always been of walking in a whole new world with you. A whole new world.
A whole new world.
That's where we'll be.
That's where we'll be.
This doesn't take a lot of adaptation, does it?
A home in space
For you and
Big ending.
Made you look.
And then like the TRAPPIST-1 system had just been discovered that was like these 7 planets around one sun. So I just wanted to throw it back there, like, you know, like this, the idea of that. I've got some comments about what that's about. It's like the idea is just because that's the last line of Aladdin, right? Is the genie coming down from the moon, like major look. And I thought it was kind of a cool connection. I don't know if it works super well, but like that science, you know, these like few scientists way back in the beginning, they were the ones that pushed for all of this to happen. And now, like at the time, like everyone was talking about it and writing articles about it, and it so easily could have, you know, it could have waited like another decade for anyone to have really pushed it, but these guys, you know, made it happen. So I thought that was good and worth a shout out for this, you know, this scientist at the end being like, "Yep, told you so." Yeah.
Made you look.
There's a lot going on in there in that ending. There's like the actual chord is like starts with a. It's like a. I think it's like a. It's like a C sus4 with a 7, but then. But like there's a whole bunch of stuff that ends up like getting put into it because I just wanted to make it sound really chaotic. Like there's like I think there's that 5th there, or like they're yeah I think that's what I was doing. That's because there's a one of the classic things you do to make something sound spacey, ever since hosts the planets, is that you have a major chord, and then a tritone away from it, you put another major chord. You put them together, and it's just like, it's a super. So this happens in the planets. It's. You'll probably be able to hear it in like the Death Star sequences in Star Wars, which took heavily from Holst's plans, like, or like, yeah, that kind of thing. So I think I was doing the same thing here, where I was trying to do like that combination. Can we hear it? Can we pull it out of there?
Made you look.
Does Kerbal do it too? Yeah, that's not surprising. It's like a music meme at this point.
Hey,
for
musical
space stuff.
scientists! This video was made possible by Google's Making and Science team.
Hey, I look pretty good in this. I like this new format for an end screen.
If you'd like to see more cool science videos, check out that playlist. Click on the faces of my collaborators to see some of their.
Oh, this is when I started doing so. Oh, look at that, the way that lines up. It's great. I started doing this is like such a weird thing to do in an end screen. These little like I had recorded a couple of like just like random little noises, and you'll hear like in the end screen I started doing I started having them be just when things would pop up.
Science team. If you'd like to see more cool science videos, check out that playlist. Click on the faces of my collaborators to see some of their amazing work. And if you'd like to support this channel like these lovely people, please consider going to patreon.com/acapellascience and pledging your support. My name is Tim Blay, and I'll be bringing you more whole new worlds of research on the next
Acapella Science.
Ha. Very nice. YouTube, I think one of the great things that YouTube ever did was enforcing 20-minute end screen or 20-second end screens. So now every time you watch one of my videos, you'll probably be aware of those pops in a way that you didn't used to. Okay.